Welcome to Cosmic Lullaby Channel. In the silent, unending expanse of the cosmos, our world is adrift in a celestial firing range. Above our heads, beyond the thin, fragile veil of our atmosphere, a silent war is waged every second of every day. We are under a constant, unrelenting bombardment. Tonight, we turn our gaze to the sky, not in search of gentle wonder, but to confront the stark reality of the cosmic giants that silently chart their courses through the void. We are tracing the paths of ancient rocks, relics from the very birth of our solar system, that have drifted through the blackness for millions, even billions of years, patiently waiting for gravity to call them home to a final, fiery conclusion. Some of these cosmic projectiles are no bigger than grains of sand, vanishing in a fleeting, incandescent blink as they surrender to the friction of our upper atmosphere. Others, however, burn with such ferocious intensity they can light up the entire sky, turning night into an eerie, momentary day. And then there are the rare few, the civilization killers, cosmic behemoths that carry the unbridled power to end worlds, to rewrite the course of life on this planet in a single cataclysmic instant. These are not merely rocks, they are messengers of fire, architects of destruction, and the unlikely catalysts of deep creation. They have carved colossal craters into the flesh of our planet, stirred the primordial oceans into chaos, darkened the skies with the dust of their impact, and irrevocably rewritten the destiny of life on Earth. For 66 million years, the reign of the dinosaurs was absolute, an era of biological dominance that seemed unshakable, until a single object, a meteor more than 6 miles wide, struck what is now the Yucatan Peninsula. The impact, known today as the Chicxulub crater, released energy on a scale that defies human imagination, a force equivalent to billions of nuclear weapons detonating at once, triggering global firestorms, seismic upheaval, and a prolonged climate shift that led to the extinction of nearly 75% of all life. This is not ancient history, it is a precedent. The threat is not hypothetical, it is embedded in the very architecture of our solar system. In 1908, a massive explosion shook the remote skies above Siberia, flattening over 800 square miles of forest near the Tunguska River with an almost unimaginable force, snapping ancient trees like matchsticks, but leaving no discernible crater. Scientists now believe this devastation was wrought by a small asteroid or comet fragment that detonated in mid-air before it could strike the ground, releasing energy equivalent to millions of tons of TNT. For years, the event was shrouded in mystery, a ghost explosion in a remote wilderness. But it stands as the largest impact event in recorded history to occur over land, a stark and powerful reminder of the destructive potential carried by even moderately sized space debris. More recently, on a quiet morning in 2013, the residents of Chelyabinsk were unwilling witnesses to this cosmic reality. A bright fireball, an object estimated to be the size of a school bus, streaked across the sky and exploded mid-air with the force of a small nuclear blast, more than 30 times stronger than the bomb that leveled Hiroshima. The resulting shockwave shattered thousands of windows, caused widespread structural damage, and injured over 1,000 people, not from direct impact, but from the flying shards of glass and debris from their own collapsing environment. The Chelyabinsk event was a geopolitical wake-up call. Captured on hundreds of dashboard cameras and mobile phones, it provided the first-ever high-fidelity, crowdsourced dataset of a significant airburst event. It forced governments and space agencies to publicly confront a threat that had long been the domain of science fiction. In its wake, international cooperation on planetary defense accelerated, with organizations like NASA's Planetary Defense Coordination Office and the United Nations-endorsed International Asteroid Warning Network gaining new urgency and funding. The invisible threat had suddenly become terrifyingly visible. Yet, to focus solely on the destructive power of these celestial visitors is to miss half of a much deeper, more profound story. These objects are not just agents of chaos. They are time travelers, physical artifacts carrying the memory of a universe that existed before our own world was born. Long before the Earth had cooled, before the oceans had formed, tiny fragments of stone and metal were already drifting through the swirling gas and dust of the newborn solar system. When scientists study the meteorites that have survived the fiery descent to our planet, they find something astonishing. Many of these fragments are over 4.5 billion years old, measurably older than the Earth itself. They are pristine samples of the solar nebula, the primordial cloud that gave birth to our Sun and all its planets. Some microscopic grains locked deep inside these meteorites may even predate our Sun entirely. Stardust, forged in the hearts of long-dead stars and cast out into the void to become the building blocks of new worlds. When you hold one of these objects, you are not merely holding a rock. The overall mood, a tangible piece of something that drifted through the cold silence of space long before there were trees, oceans, or a sky to fall from. You are connecting with the very genesis of our cosmic home, and this connection is more intimate than we could ever imagine. Every single day, our planet is silently dusted with more than 100 tons of this debris from space. A constant, gentle rain of micrometeorites, so small they float through our atmosphere and settle almost unnoticed on rooftops, in forests, and across the vast oceans. These are the remnants of asteroids and comets, and right now, at this very moment, some of them are floating in the air around you. You have, without question, breathed in a piece of outer space without ever knowing it. A silent reminder that the boundary between Earth and the cosmos is not a distant line in the sky, but a permeable frontier that is falling softly all around us, all the time. For millennia, humanity has looked to the night sky and seen them, fleeting streaks of light we call shooting stars. We have woven them into our myths, wished upon them in moments of hope, and seen them as gentle omens, celestial teardrops from the heavens. But this romantic vision is a profound misunderstanding of a far more violent and extraordinary truth. What we witness in that brief, beautiful flash is not a star falling from its celestial perch, but the final, fiery death of a traveler from the void. It is the last moment of a journey that may have lasted for eons, ending in a catastrophic collision with our world's atmospheric shield. The object itself, the meteoroid, is often astonishingly small. A fragment of rock or metal frequently no larger than a pebble, sometimes barely the size of a grain of rice. Yet this minuscule projectile is hurtling into our atmosphere at almost unimaginable speeds, traveling between 20 and 70 kilometers per second, which can be upwards of 150,000 miles per hour. At such velocities, even the fastest jet aircraft on Earth would seem to be standing still. It is this incredible kinetic energy that transforms a silent, cold rock into a spectacular blaze of light. The phenomenon is not one of simple friction, as is commonly believed. Rather, as the meteoroid plummets into the upper atmosphere, it compresses the air in front of it with such extreme force that the air itself is heated to thousands of degrees. This process, known as ram pressure, is so intense that it doesn't just heat the rock, it transforms the very air around it. The molecules of nitrogen and oxygen are stripped of their electrons, creating a glowing, incandescent envelope of plasma that encases the meteoroid. What we see as a shooting star is not the rock itself burning, but this superheated sheath of ionized gas, a line of fire drawn across the sky by nothing more than speed and pressure. The vast majority of these atmospheric entries go completely unnoticed. For every visible meteor that streaks across the night sky, countless others burn up in fractions of a second, so fast and so faint that they are invisible to the human eye. Earth is under a constant invisible siege, and our atmosphere is a relentless active defense system. Almost none of the cosmic debris that bombards our planet actually reaches the ground. Most of it, the fine dust that constitutes the majority of the 100 tons of material we collect daily, is completely vaporized high in the sky. Even now, somewhere in the darkness above you, another tiny object may be entering the atmosphere, glowing softly for a moment before fading into nothingness, a silent visitor that came and went without witness. However, when something larger enters the sky, the event is anything but silent. These are the fireballs or bolides, meteors so bright they can outshine the full moon, cast moving shadows on the ground, and be seen from hundreds of miles away. A fireball is simply a meteor that refuses to be subtle. As it tears through the atmosphere, the intense pressure can build to a critical point. For some larger fragments, the structural integrity of the rock can no longer withstand the immense forces acting upon it. The result is a sudden, catastrophic mid-air detonation, a brilliant flash of light that can briefly illuminate the entire landscape. These bolide events, like the one over Chelyabinsk, can release energy equivalent to a nuclear blast. The shock wave they produce can be powerful enough to rattle windows and trigger sensitive seismic sensors on the ground, literally making the Earth ring like a bell. This constant celestial traffic has not gone unnoticed by global powers. In a world acutely aware of airborne threats, the detection of high-energy atmospheric events is a matter of strategic importance. The same network of military satellites designed to detect the heat signature of a ballistic missile launch or a clandestine nuclear test are also perfectly capable of spotting the brilliant flash of a large fireball. For decades during the Cold War, this data was highly classified, a closely guarded secret of competing superpowers. Today, while still monitored for national security, much of this information is shared with the international scientific community. Furthermore, a global network of infrasound stations, originally established to monitor compliance with the Comprehensive Nuclear Test Ban Treaty, constantly listens for the low-frequency sound waves produced by these mid-air explosions, sounds that are far below the range of human hearing but travel for thousands of miles. This network can pinpoint the location, altitude, and energy release of a bolide with remarkable precision. What was once a system of geopolitical surveillance has been repurposed into a vital tool for planetary defense and atmospheric science, a testament to a shifting global perspective where the shared threat from the cosmos begins to overshadow terrestrial rivalries. The light from these events carries its own coded information. The color of a meteor's glow is a form of real-time chemical analysis, a celestial autopsy written in fire. As the rock vaporizes, its constituent elements emit light at specific wavelengths when heated. Sodium, a common element, produces a bright orange or yellow streak. Iron and nickel, the building blocks of planetary cores, often produce a brilliant yellow-white light. Magnesium glows with a piercing white intensity, while calcium can appear as a ghostly violet. Perhaps most strikingly, the presence of nickel and iron interacting with the Earth's own atmospheric gases can create a vivid, almost neon green hue, a rare and unforgettable sight. In a single, fleeting moment, a burning stone reveals its deepest secrets, telling us what it is made of and offering clues to the composition of the long-lost parent body from which it came. The silent, beautiful wish upon a star is, in reality, the final violent scream of an ancient rock, consumed by a sheath of plasma in the upper atmosphere. Its elemental signature, a final broadcast across the dark canvas of the night. When the fire in the sky fades and the momentary thunder of a bolide shockwave dissipates into silence, the event is not always over. For a select, infinitesimally small fraction of these cosmic invaders, the journey does not end in a flash of vaporized dust. A fragment, or sometimes many, will survive the brutal ordeal of atmospheric entry, decelerate from hypersonic speeds, and complete the final stage of their fall under the simple pull of gravity. These are the survivors, the tangible messengers. They are the meteorites, and their arrival on Earth marks the end of one journey and the beginning of another, a journey into the hands of science and, increasingly, into a high-stakes global market. One of the most astonishing truths about these objects is their state upon arrival. Despite having blazed through the atmosphere encased in a sheath of superheated plasma, many meteorites that survive the fall are found cold to the touch. The intense heat of entry only affects the outermost surface, a process called ablation that lasts for mere seconds. This creates a thin, dark, glassy coating known as a fusion crust, the unmistakable scorch mark of a rock that has fallen through fire. But beneath this veneer, the interior of the stone remains insulated, still retaining the deep, profound cold of interplanetary space, where it has spent millions or even billions of years. Eyewitnesses who have been first to a fresh fall have reported seeing frost form on the meteorite's surface as it acclimates to the moisture and warmth of Earth's environment. The overall mood still carries the memory of the freezing void. Once on the ground, these objects become more than mere curiosities. They are Rosetta Stones that allow us to decipher the birth of our solar system. Scientists classify them into three main categories, each telling a different story of cosmic evolution. The most common are the stony meteorites, which are themselves divided into many subgroups, but are largely composed of silicate minerals, similar to the rocks of Earth's own crust. These are often the most ancient, containing tiny spherical grains called chondrules, droplets of molten rock that cooled and crystallized in the solar nebula before the planets had even formed. But it is the other types that reveal the violent, dynamic processes that shaped young worlds. The iron meteorites are fragments of the very hearts of ancient protoplanets. In the early solar system, many large asteroids were massive enough for their interiors to melt and differentiate, allowing heavy materials like iron and nickel to sink to the center and form metallic cores, just as Earth did. Subsequent catastrophic collisions shattered these nascent worlds, flinging pieces of their now solidified metal cores into space. When one of these fragments is sliced open, polished, and etched with a mild acid, it often reveals a stunning, intricate crystalline pattern of interlocking metallic bands. This is the Widmanstätten pattern, and it is the undeniable signature of an extraterrestrial origin. These structures can only form when molten iron and nickel cool at an astonishingly slow rate, no more than a few degrees per million years, a process that is only possible in the zero-gravity, vacuum environment of a celestial body's core. No earthly process can replicate it. To touch an iron meteorite is to touch the exposed, shattered heart of a world that once was. Rarer still are the messages from our closest celestial neighbors. Not all meteorites originate in the asteroid belt between Mars and Jupiter. Some have been blasted off the surfaces of the Moon and even Mars by massive impacts. The energy of these collisions can be so immense that it ejects surface material into space with enough velocity to escape the parent body's gravity, sending it on a long, wandering journey across the solar system. For thousands or millions of years, these rocks drift until their orbits eventually intersect with Earth. Lunar meteorites are identified by their unique chemical and mineralogical fingerprints, which are a perfect match for the rock samples brought back by the Apollo missions. Even more precious are the Martian meteorites. For now, they remain the only physical samples of the red planet that we possess. They are, in effect, free sample return missions delivered by nature. Within some of these Martian rocks, scientists have discovered tiny, microscopic bubbles of trapped gas, and analysis of this gas reveals a composition identical to the atmosphere of Mars, as measured by our robotic landers. These fragments are of incalculable scientific and geopolitical value. As nations like the United States, China, and others plan for future crewed missions to Mars, the data gleaned from these rocks on mineral composition, water history, and potential for past microbial life is fundamentally shaping the exploration of another world. This immense value has given rise to a fiercely competitive and often secretive global market. Meteorite hunters, modern-day prospectors, scour the deserts of Northwest Africa, the dry lake beds of the American Southwest, and the vast icy plains of Antarctica in search of these fallen treasures. A natural male meteorite might sell for a few dollars per gram, but a slice of a palisite, a stunning stony iron meteorite embedded with gem-like olivine crystals, can command a small fortune. And for a verified piece of the Moon or Mars, the price can skyrocket into the hundreds of thousands or even millions of dollars, depending on the size and scientific importance. Auction houses like Christie's and Sotheby's now hold regular sales of these cosmic artifacts, where they are sold alongside fine art and dinosaur fossils. This has created a profound tension between the worlds of private collection and public science. While collectors are drawn to the aesthetic beauty and the romance of owning a piece of another world, scientists worry that invaluable data is being lost as scientifically crucial specimens disappear into private vaults, never to be studied. The question of ownership itself is a legal gray area, a subject of international debate. When a rock falls from the sky, who owns it? The owner of the land where it fell? The person who found it? Or does it belong to the nation, a piece of celestial heritage for all of humanity? As of now, the answer changes depending on where you stand, turning these messengers from space into objects of terrestrial conflict and commerce. While the fall of a solitary meteorite is a shocking, unpredictable intrusion of the cosmos into our terrestrial world, there are other celestial encounters that are anything but random. These are the annual appointments our planet keeps with the ghosts of the solar system. We know them as meteor showers. For a few nights each year, the heavens open up, putting on a display that can range from a gentle sprinkling of light to a torrential downpour of fire. These events may feel spontaneous, but they are among the most predictable phenomena in the night sky, the result of the Earth, in its ceaseless orbit around the Sun, passing through invisible rivers of dust and debris left behind by another cosmic traveler, the comet. As a comet, a vast ball of ice, rock, and frozen gases makes its long journey toward the Sun, it is heated by solar radiation. This process causes its icy body to shed material, casting off a trail of tiny fragments, particles of rock and dust, many no bigger than grains of sand, that remain suspended in its orbital path. This creates a long, invisible ribbon of debris that stretches for millions of miles across the solar system. And each year, as Earth's own orbit intersects one of these ancient trails, we plow directly through it. The result is a meteor shower. The dozens, sometimes hundreds of tiny particles slam into our atmosphere at colossal speeds and burn up in bright, parallel streaks of light. What appears to us as a magical, spontaneous show is, in fact, the quiet, predictable echo of a comet's ancient passage. Astronomers have mapped these debris streams with incredible precision, linking each major shower to its parent body. Every August, Earth drifts through the dense trail of particles left by Comet Swift-Tuttle, creating the Perseid meteor shower, one of the most brilliant and reliable displays of the year. In November, we encounter the debris of Comet Tempel-Tuttle, which gives us the Leonid shower, an event with a reputation for producing some of the most spectacular meteor storms in recorded history. And in December, we pass through the trail of 3200 Phaethon, an object that blurs the line between a rocky asteroid and an active comet, to witness the Geminids. The naming of these showers comes from a simple trick of perspective. From our vantage point on Earth, all the meteors in a particular shower appear to stream away from a single point in the sky, known as the radiant. This point is named for the constellation it appears in. The Perseids radiate from Perseus, the Leonids from Leo. It is a celestial illusion, but it provides a useful guide for stargazers, a reminder that even the briefest flash of light has a place it seems to call home. But this predictable, beautiful display is a double-edged sword. The same parent bodies that give us these breathtaking nights of falling stars represent one of the greatest long-term threats to our existence. Comet 109P/Swift-Tuttle, the source of the annual Perseid shower, is not some distant, harmless snowball. It is a colossal object with a nucleus estimated to be 26 kilometers, 16 miles in diameter, more than twice the size of the object that wiped out the dinosaurs. Its orbit is highly elliptical, bringing it across Earth's path roughly every 133 years. Because of its size and its orbit's proximity to our own, Swift-Tuttle is classified by NASA and other international space agencies as a potentially hazardous object, perhaps the single most dangerous object known to humanity. While current calculations show no risk of impact for at least the next 2 millennia, the orbital mechanics of comets are notoriously difficult to predict over long timescales. A slight nudge from another planet's gravity could, in the distant future, alter its path with catastrophic consequences. The annual Perseid shower, therefore, is more than just a light show. It is a beautiful yet deeply unsettling reminder that our planet shares its orbital space with a dormant civilization killer. This stark reality fuels the global imperative for planetary defense, driving international collaborations to track and characterize every known near-Earth object, an expensive and technologically demanding effort that operates silently in the background of our daily lives. The historical impact of these showers has been just as profound. In the pre-dawn hours of November 13, 1833, the Leonid meteor shower produced a celestial event so overwhelming it became known as the night the stars fell. Earth passed through a particularly dense filament of cometary debris, and the sky erupted. Eyewitnesses from across North America described a storm of fire with estimates of over 100,000 meteors streaking across the sky in a single night, so many that they appeared to fall like snowflakes in a blizzard. The event caused widespread panic and was interpreted by many as a divine sign or the end of the world. But for the scientific community, it was a moment of revolutionary insight. The sheer scale and directional consistency of the storm provided the first conclusive evidence that meteor showers were an astronomical phenomenon originating from beyond Earth's atmosphere. It directly led to the discovery of the link between the debris streams and the orbits of comets, shattering the old Aristotelian view of a perfect, unchanging heaven and replacing it with the modern understanding of a dynamic, debris-filled, and sometimes hazardous solar system. In a very real sense, our entire field of meteor science was born from the terror and wonder of that single night. Today, the economic footprint of this celestial clockwork is undeniable, having spawned a thriving industry of astrotourism. Each year, thousands of people travel to designated dark sky preserves and remote national parks, far from the light pollution of cities, to witness the peak of showers like the Perseids. This influx of visitors provides a significant economic boost to rural communities, filling hotels, restaurants, and campgrounds, all in pursuit of a clear, unobstructed view of the cosmos. An entire ecosystem of products, from high-end camera lenses to sophisticated stargazing apps, sees a surge in sales, all driven by the predictable annual passage of our planet through the fossilized remnants of a comet's tail. Beyond the sheer physical power of cosmic impacts and the predictable clockwork of meteor showers lies a far more profound and intimate connection between our world and the debris that falls from the sky. For within a very special class of these celestial messengers, scientists have discovered something that challenges the very definition of our terrestrial origins. They have found the building blocks of life itself. To understand this, we must look beyond the dense metallic fragments of planetary cores or the common stony meteorites. Our focus turns to a rarer, more fragile type of visitor, the carbonaceous chondrites. These are some of the most primitive objects in our solar system, dark, crumbly stones rich in water and carbon-based compounds. They are, in essence, pristine 4.5 billion-year-old samples of the raw material from which the planets were made. And locked within their dark, ancient matrix is a revelation that has revolutionized the fields of biology and chemistry. They contain organic molecules, not signs of alien biology, but the fundamental chemical ingredients that life as we know it requires to begin. This is not speculation, it is a repeatedly verified scientific fact. The watershed moment for this field of science occurred on September 28, 1969, near the small town of Murchison, Australia. Residents witnessed a brilliant fireball that broke apart with a loud tremor, scattering over 100 kilograms of dark, strange-smelling stones across the countryside. The overall Murchison meteorite fragments was a stroke of scientific fortune as it minimized their exposure to terrestrial contamination. When analysts at NASA and other institutions began studying its composition, they found something that would change the course of science. The Murchison meteorite was teeming with amino acids, the essential molecules that link together to form proteins, the very workhorses of all living cells. Over 90 different types of amino acids have since been identified within its fragments, many of which are exceedingly rare or entirely absent in Earth's biology. This was the smoking gun. The unique extraterrestrial nature of these amino acids proved they were not the result of earthly contamination after the fall. They had formed in space, within the meteorite's parent body, an ancient asteroid drifting in the cold void billions of years ago. This discovery gave credible physical evidence to a long-debated theory known as panspermia. In its modern form, this hypothesis suggests that during Earth's violent infancy, in its first billion years, the constant bombardment by comets and meteorites was not just a destructive force, but also a creative one. These falling space rocks could have acted as a planetary delivery service, seeding the sterile primordial oceans of the young Earth with the complex organic compounds necessary to jumpstart biology. Our planet, in this scenario, was not an isolated biological miracle. Instead, it was gifted a crucial chemical head start from the cosmos. The Murchison meteorite and others like it suggest that the chemistry leading to life is not unique to Earth. It happens naturally in the cold, irradiated environment of space, on the surface of asteroids, and in the swirling clouds of gas and dust between the stars. The ingredients for life, it seems, are a common feature of the cosmic landscape. This profoundly changes our perception of our place in the universe. Life on Earth may not be a one-off accident, but the predictable outcome of universal chemical laws, given the right delivery system and a suitable planetary incubator. The quest to verify and expand upon this paradigm-shifting discovery is a primary driver of some of the most ambitious and expensive space missions ever undertaken. While meteorites like Murchison are invaluable, they are inevitably compromised to some degree by their violent passage through our atmosphere and contact with our biosphere. The scientific holy grail is to obtain a pristine, untouched sample of a carbon-rich asteroid and return it to Earth. This is the explicit goal of multi-billion-dollar, geopolitically significant missions like NASA's OSIRIS-REx and the Japan Aerospace Exploration Agency's Hayabusa 2. In 2020, OSIRIS-REx successfully collected a sample from the surface of Bennu, a dark, primitive, carbonaceous asteroid, and returned it to Earth in 2023. The ongoing analysis of this material represents a new frontier in the search for our origins. Scientists are studying these grains of asteroid, untouched since the dawn of the solar system, in the hope of finding the full suite of prebiotic molecules that could have seeded Earth. This is a new kind of space race, one focused not on planting flags, but on answering the most fundamental question of our existence, a race in which the competing space agencies of the world hold pieces to the same profound puzzle. This cosmic delivery system may have brought even more than just the building blocks of proteins. The oldest known materials ever studied by humanity did not come from the deepest recesses of our own planet. They came from the sky. Within some meteorites, scientists have found microscopic, resilient grains of stardust, pre-solar grains that formed inside ancient dying stars long before our own sun ignited. These tiny specks of diamond, graphite, and silicon carbide are over 7 billion years old, time travelers from a different stellar epoch. They were blown out into space, drifted through the interstellar medium for billions of years, and were eventually incorporated into the solar nebula that formed our own solar system. They are a direct physical link to the ancestral stars that forged the heavy elements of which we are made. When a meteorite delivers these ancient grains to Earth, it is a reminder that the boundary between geology, biology, and astronomy is an artificial one. The sky did not just shape our planet with craters, it may well have seeded it with the potential for life and delivered the very stardust that now flows through our veins. The profound revelations locked within these fallen stones, from the secrets of planetary formation to the very chemical origins of life, have ignited a global scientific treasure hunt. But finding these cosmic messengers is an immense challenge. The vast majority of meteorites that reach the Earth's surface fall unnoticed into oceans, which cover over 70% of our planet, or land in remote, inaccessible jungles and mountain ranges, lost forever. Others that fall in more temperate climates are quickly subjected to weathering. Rain, wind, and chemical erosion begin to break them down, erasing their fusion crusts and contaminating their interiors, slowly turning them into indistinguishable terrestrial rocks. To find a truly pristine, well-preserved sample, scientists and prospectors must travel to the most extreme environments on Earth, places where the relentless forces of decay are held in check. A natural male narrator with a warm, friendly tone. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. And one location stands above all others as the single greatest repository of fallen space rocks on the planet, the frozen, desolate continent of Antarctica. It may seem a paradox, but this vast, icy wasteland is a paradise for meteorite hunters, a natural treasure chest where cosmic artifacts are collected and preserved with unparalleled efficiency. The unique environment of Antarctica makes it an ideal collection ground for several reasons. Firstly, the extreme cold and dry conditions act as a perfect preservative, shielding the meteorites from the chemical and water erosion that would quickly degrade them elsewhere. A rock that fell 1,000 years ago can appear as fresh as one that fell yesterday. Secondly, the stark white landscape of the ice sheet makes the dark fusion-crusted meteorites stand out in dramatic contrast, making them far easier to spot than in a forest or a field. But the most crucial factor is the continent's own geology and the slow, inexorable movement of its ice sheets. Over millennia, as snow falls and compacts into ice, any meteorites that have landed on the surface are buried and carried along with the glacial flow. When these ancient rivers of ice encounter a barrier, such as the submerged peaks of the transantarctic mountains, the ice is forced upwards. Here, fierce, relentless winds, known as katabatic winds, sweep down from the polar plateau, eroding the rising ice and sublimating it directly from a solid to a gas. This process, over thousands of years, acts as a natural conveyor belt, exhuming the meteorites that were once buried deep within the ice and concentrating them on the surface in specific areas known as blue ice stranding zones. These stranding zones are the primary targets for international scientific expeditions. Each year, government-funded programs, most notably the American Antarctic Search for Meteorites ANSMET program, as well as teams from Japan, China, and various European nations, venture into the deep Antarctic field. The work is grueling and dangerous. Teams of scientists live in tents in temperatures that can plunge far below freezing, methodically sweeping across the blue ice on snowmobiles in precise grid patterns. When a potential meteorite is spotted, it is treated with the reverence of an archaeological artifact. Its location is logged by GPS, it is photographed in situ, and it is collected using sterile tools to prevent any contamination from human hands. The samples are then carefully sealed and kept frozen for their long journey back to specialized curation facilities, like the one at NASA's Johnson Space Center. This highly organized, publicly funded effort stands in stark contrast to the commercialized, competitive gold rush mentality of meteorite hunting in the deserts of Africa and Oman. Under the terms of the Antarctic Treaty, the continent is designated as a scientific preserve, a place for peace and international cooperation. There is no private ownership of Antarctic meteorites. They are considered the property of all humankind, held in trust by the scientific community for research and study. This international protocol has made Antarctica the source of the single largest collection of meteorites in the world. To date, tens of thousands of individual specimens have been recovered from the ice, representing a statistical sample of the debris in our solar system that is unmatched by any other location. This vast library of stones has been the source of countless breakthroughs, including the identification of some of the first lunar and Martian meteorites, which were found on the ice long before their origins could be confirmed by robotic missions. The continent's pristine conditions have preserved not just the rocks themselves, but the delicate organic molecules and volatile compounds within them, providing astrobiologists with their cleanest look yet at the prebiotic chemistry of the cosmos. In a world often driven by competition for resources, the scientific exploration of Antarctica represents a different model, one of collaboration, careful preservation, and shared discovery. The frozen continent acts as a silent, impartial curator, collecting messengers from space for millennia and holding them in its icy grip until they can be gently lifted into a scientist's gloved hand, their priceless stories of cosmic history still perfectly intact. While the scientific treasures recovered from the Antarctic ice offer an intimate, handheld connection to the cosmos, the evidence of our planet's most violent encounters with space is written on a scale that is difficult to comprehend. These are the colossal scars etched into the very crust of the Earth, impact craters. They are the fossilized wounds from a time when the solar system was a far more chaotic and dangerous place, and they stand as silent monuments to events of unimaginable power. Yet, finding these scars is a profound challenge. Our planet is a living, breathing world, dynamic and restless. The relentless forces of erosion, wind, water, and ice work tirelessly to wear down mountains and soften landscapes. Plate tectonics constantly recycles the crust, subducting old rock and creating new land. Over millions of years, these processes conspire to erase all but the most recent or the most massive of these impact structures, leaving behind ghostly, almost invisible outlines that can only be detected through advanced geological surveys and satellite imaging. To identify these ancient wounds, scientists have become planetary forensic experts, hunting for a unique and indelible fingerprint that no terrestrial process can replicate: shock metamorphism. When a large body strikes the Earth at cosmic velocities, it generates pressures and temperatures far greater than any volcanic eruption. This immense shock wave blasts through the target rock, permanently altering the crystalline structure of its minerals in a fraction of a second. It creates microscopic features like shocked quartz, a mineral whose crystal lattice has been uniquely deformed into parallel planes. This is the geological smoking gun. Finding shocked quartz at a suspected site is the ultimate proof of a hypervelocity impact, allowing geologists to confirm the existence of a crater long after its walls have eroded to nothing. The most infamous of these structures, the Chicxulub crater in Mexico, is the tombstone of the dinosaurs. Buried beneath 66 million years of sediment, its vast 180-kilometer-wide outline is completely invisible from the ground. Only through gravity and magnetic surveys, and later satellite data, was its full, terrible scale revealed. Today, this buried scar is not just a historical relic, it is an active international scientific laboratory. Through the International Ocean Discovery Program, a multi-billion-dollar collaboration involving scientists and funding from dozens of nations, researchers have drilled deep into the crater's peak ring, the circular ridge of mountains that rebounded in the moments after impact. The core samples they retrieved are a geological time machine, providing a second-by-second account of a planetary-scale apocalypse. They show how solid granite was briefly turned into a fluid, how a world-circling tsunami was generated, and how the dust and sulfur ejected into the atmosphere plunged the Earth into a dark, cold winter that precipitated a mass extinction. This is more than just paleontological curiosity. A natural male narrator voice with a warm, friendly tone. It is a vital exercise in understanding the intricate feedback loops of our planet's climate system, providing crucial data for modeling the potential consequences of modern global catastrophes, from a nuclear winter to the effects of our own changing climate. In a strange and profound twist of cosmic fate, these sites of ultimate destruction have also become sources of immense economic wealth. Some of the most valuable mineral deposits on Earth are located within or are a direct result of ancient impact structures. The Sudbury Basin in Ontario, Canada, is the site of a massive impact that occurred 1.8 billion years ago. The energy of the collision was so great that it melted a vast section of the Earth's crust, creating a sea of magma 3 kilometers deep. As this melt sheet slowly cooled, heavy, valuable metals like nickel, copper, platinum, and palladium, essential components in everything from stainless steel to electric vehicle batteries, sank and became concentrated at the bottom. Today, the Sudbury Basin is one of the world's largest and richest mining districts, a multi-billion-dollar economic engine that is a direct legacy of a cataclysmic celestial event. Similarly, the Vredefort Dome in South Africa, the largest and oldest confirmed impact structure on Earth, is situated in a region that has produced more gold than any other in human history. The impact is thought to have played a critical role in the geological processes that made these vast gold deposits accessible. These craters are not just scars, they are geological engines that have, in a violent act of creation, gifted humanity with a portion of its most critical strategic resources, shaping global trade and the wealth of nations. To truly appreciate the protective role of our planet's active geology, we need only look to our nearest neighbor. The Moon has no thick atmosphere to burn up incoming projectiles, and no wind or water to erase the scars. It is, in essence, a celestial museum of violence. Its surface covered in a dense tapestry of craters that record billions of years of relentless bombardment. Every impact, large or small, is preserved in near perfection. The face of the Moon is a stark portrait of what our own world would look like without its atmospheric shield and its dynamic healing crust. Every crater on Earth, therefore, represents an event that was powerful enough to overcome all of our planet's defenses. They are the exceptions, the survivors. They have become lakes of perfectly clear, deep water, like Lake Manicouagan in Quebec, a vast annular lake that traces the outline of a 214-million-year-old impact. They have triggered earthquakes that shook continents and tsunamis that washed across oceans. They have flash-melted surface rock into fields of natural glass called tektites, which are blasted hundreds of miles from the impact site. These scars are a fundamental part of our planet's story, a violent and recurring chapter that has reshaped landscapes, altered the course of evolution, and, paradoxically, forged a portion of the very wealth that fuels our modern world. The scars etched into our planet and the pockmarked face of the Moon serve as a constant sobering reminder of the existential threat that lurks in the cosmos. For most of human history, we have been passive observers, living at the mercy of a celestial lottery, unaware of the colossal forces that could end civilization in an instant. But we are now living in a pivotal moment. The first time in the 4.5 billion year history of life on Earth that a species has developed the awareness and the technological capability to not just understand this threat, but to actively defend itself against it. We have entered the age of planetary defense. This is not science fiction. It is a rapidly evolving, globally coordinated effort to identify, track, and ultimately neutralize the danger posed by near-Earth objects, or NEOs. At the forefront of this endeavor are sophisticated, ground-based, and spaceborne survey programs, the silent sentinels of our solar system. Telescopes like the Pan-STARRS in Hawaii and the Catalina Sky Survey in Arizona are engaged in a relentless nightly search, scanning the skies and cataloging thousands of asteroids and comets whose orbits bring them into Earth's neighborhood. Each new discovery is logged, its trajectory calculated and refined, and its risk to Earth assessed by organizations like NASA's Jet Propulsion Laboratory and the European Space Agency's Near-Earth Object Coordination Center. This global effort operates under a stark and unforgiving timeline. Finding a potentially hazardous object is meaningless if it is found too late. The primary goal is to create a comprehensive catalog of all NEOs large enough to cause significant damage, ideally with decades of warning time before any potential impact. An object in the 140-meter class, while not an extinction-level threat, could obliterate a city and cause regional devastation. The international scientific consensus, endorsed by the United Nations, is that finding 90% of these objects is a minimum requirement for planetary security. This has driven a technological and geopolitical race to build the next generation of survey telescopes. The Vera C. Rubin Observatory, under construction in Chile, is poised to revolutionize the field. Its massive camera capable of imaging the entire visible sky every few nights. NASA is also developing the NEO Surveyor, a space-based infrared telescope that will be positioned between the Earth and the Sun. From this vantage point, it will be able to detect asteroids that are currently impossible to see from Earth, particularly those that approach from the direction of the Sun, a notorious blind spot that hid the Chelyabinsk meteor until it was too late. The cost of these programs runs into the billions of dollars, a significant investment in what is essentially a planetary insurance policy. The economic calculation is brutally simple. The cost of prevention, however high, is infinitesimally small compared to the cost of an impact, which would be measured not just in trillions of dollars, but in the potential collapse of modern civilization. But finding the threat is only the first step. The ultimate challenge is knowing what to do about it. The field of impact mitigation is now moving from theoretical models to real-world experimentation. The dominant strategy is not to destroy an incoming asteroid, which could create a deadly shotgun blast of smaller fragments, but to deflect it. This requires subtly altering the object's velocity by a tiny amount, years in advance, allowing that small change to compound over its long orbital path so that it safely misses the Earth. In a landmark demonstration of this capability, NASA conducted the Double Asteroid Redirection Test, or DART mission. In 2022, the DART spacecraft, traveling at over 14,000 miles per hour, deliberately slammed into Dimorphos, a small moonlet orbiting the larger asteroid Didymos. The mission was a resounding success. The overall mood measurably altered Dimorphos's orbit, proving for the first time that humanity has the technology to physically move a celestial body in a controlled and predictable way. This was a watershed moment, not just for a single space agency, but for our entire species. The data from the DART mission is being shared globally, providing a critical baseline for future deflection missions that may one day be mounted by a consortium of nations in response to a real threat. Other, more powerful deflection concepts are also under study, including the use of a gravity tractor, a heavy spacecraft that would fly alongside an asteroid for years, its tiny gravitational pull slowly tugging the object onto a new course. Or, in the most dire of circumstances, the use of a nuclear device, not to shatter the asteroid, but to detonate at a distance, using the blast's radiation to vaporize the surface and create a powerful rocket-like thrust. The development and potential deployment of such technologies, particularly nuclear options, are fraught with immense geopolitical complexity, requiring unprecedented levels of international trust and agreement. The question of who would authorize such a mission and under what circumstances is a subject of intense debate at the highest levels of international law and diplomacy. We are, in essence, building the fire brigade before the fire starts. a global effort to ensure that, unlike the dinosaurs, we will have a choice in our own destiny. And so, our journey through the hidden life of meteors, a story written in fire and stone, comes to a close. We have traveled from the silent, frozen plains of Antarctica, where scientists unearth messengers from the dawn of time, to the buried, colossal scars of Chicxulub, where an international coalition drills into the history of a planetary apocalypse. We have witnessed the violent, split-second death of a shooting star, a pebble from space consumed in a blaze of plasma. And we have contemplated the almost unimaginable patience of a Martian rock wandering the void for millions of years before finding its way to our world. We have seen how these celestial objects are not merely scientific curiosities, but drivers of our economy, catalysts for geopolitical cooperation, and, most profoundly, the possible couriers of the very chemical building blocks that allowed life to awaken on this planet. What began as a look into the night sky has become a deep and unflinching look at ourselves, our profound vulnerability, our burgeoning ingenuity, and our inescapable connection to the cosmos. For most of our existence, we have lived under what Carl Sagan called the cosmic shooting gallery, unaware of the forces that have shaped our past and could, at any moment, determine our future. The sky was a realm of gods and myths, a beautiful but inscrutable ceiling above our world. The era is now over. The Chelyabinsk event in 2013 was not just an explosion. It was the moment the veil was torn away for the modern world. The hundreds of dashboard cameras and security feeds that captured the event created an irrefutable, data-rich portrait of our vulnerability. The threat was no longer an abstract calculation based on craters and geological records. It was a visceral, shared global experience. In its aftermath, the quiet work of planetary defense was thrust from the quiet halls of academia and government agencies into the public consciousness. The DART mission's successful deflection of an asteroid was more than a technological milestone. It was a declaration of intent. It was the moment our species graduated from being passive inhabitants of a dangerous world to active guardians of our own survival. This newfound capability, however, brings with it a heavy and complex responsibility. The technologies we develop to deflect an asteroid could, in theory, be used to weaponize one. The international agreements required to act on a credible threat will test the limits of our global diplomacy. We are, in effect, building a planetary immune system, and in doing so, we are being forced to mature as a species, to recognize that a threat to any nation from the cosmos is a threat to all nations. But even as we build our shields and scan the heavens for danger, we must not lose sight of the deeper wonder. We must remember that the same cosmic processes that pose a threat are also the source of our creation. Every meteor shower graces our night sky. We are witnessing the gentle, fiery remnants of a comet's journey, a beautiful echo of the same delivery system that may have seeded our young planet with water and the ingredients for life. The iron in our blood, the calcium in our bones, the very carbon that forms the basis of our biology, all of it was forged in the hearts of stars that lived and died long before our sun was born. Meteorites are the final physical delivery of that stellar legacy. They are tangible proof that we are not separate from the universe. We are a direct, living embodiment of it. Every falling star is a reminder that the cosmos is not a distant, sterile void, but a dynamic, interconnected system in which we are an active and, for the first time, a conscious participant. We live on a quiet planet, spinning softly beneath a sky that never stops moving. A sky that is constantly touching us, reshaping us, and reminding us of our origins. The journey is far from over, The watch must continue. But for the first time, we look up not just with fear or wonder, but with the quiet confidence of a species that is finally, after millions of years, learning to read the messages in the sky and write its own story among the stars. We are living in an extraordinary era, a time when humanity's relationship with near-Earth objects is undergoing a fundamental transformation. From passive observers recording streaks of light in the sky and studying rocks that happen to fall to Earth, we are becoming active participants. No longer do we simply wait for the cosmos to come to us, we are reaching out to meet it. The overall mood is relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The overall tempo should be around 0.90. This shift is most clearly embodied in ambitious and complex space missions, designed not only to observe, but to touch, collect, and return pristine samples from asteroids. It is the next revolutionary step after studying meteorites, a deliberate effort to retrieve missing pages of the solar system's chronicle, unaltered by the fiery passage through our atmosphere. At the forefront of this daring field is the Japan Aerospace Exploration Agency, JAXA, with its groundbreaking Hayabusa missions. The first Hayabusa mission, launched in 2003, was a high-risk technological experiment with a seemingly impossible goal: to reach the potato-shaped asteroid Itokawa, land on its surface, collect a sample, and bring it back to Earth. Hayabusa's journey became an epic tale of engineering and perseverance. The spacecraft faced countless challenges that could have ended the mission. A massive solar storm damaged its solar panels. Several reaction wheels used for navigation failed, and a dramatic landing attempt left the spacecraft crippled and silent for weeks. Most assumed it was lost forever. Yet Japanese engineers showed remarkable persistence, re-establishing contact and nursing the weakened craft through its long journey home. In 2010, after 7 years in space, Hayabusa's sample capsule blazed through Earth's atmosphere and landed in the remote Australian outback. Inside, scientists discovered about 1,500 tiny dust particles from Itokawa's surface. Though minuscule in quantity, this marked the first time in history that humanity had deliberately returned a sample from an asteroid. Analysis of the grains yielded unprecedented insights into space weathering, the process by which airless bodies are altered by solar wind and micrometeorite impacts, confirming that common chondrite meteorites found on Earth originate from S-type asteroids like Itokawa. Building on this hard-won success, JAXA launched Hayabusa 2 in 2014, this time targeting a different, more carbon-rich asteroid, Ryugu. Equipped with lessons from its predecessor, Hayabusa 2 was a far more advanced and complex mission. Not only did it collect surface samples, but it also carried out a bold experiment, deploying a copper impact projectile to blast an artificial crater into Ryugu's surface. The spacecraft then maneuvered skillfully to gather material ejected from beneath the surface, samples shielded from harsh solar radiation and potentially containing more pristine organic compounds. In December 2020, Hayabusa 2 successfully delivered its sample capsule back to Earth, containing over 5 grams of dark, carbon-rich material. Early analyses stunned the scientific community. Ryugu's samples held a wide variety of amino acids and other complex organic molecules, providing the strongest evidence yet that the building blocks of life formed in space and were delivered to early Earth by asteroids. Meanwhile, NASA pursued a similar goal with the OSIRIS-REx mission, targeting Bennu, another carbon-rich asteroid, thought to harbor organic molecules and water-bearing minerals. When OSIRIS-REx arrived at Bennu in 2018, it found a world full of surprises. Instead of a smooth, sandy beach-like surface, Bennu was a jumbled rubble pile, bristling with jagged boulders. This turned the planned touch-and-go, tag, sample collection into a high-stakes precision maneuver. In October 2020, the spacecraft carefully extended its robotic arm into a small crater, fired a burst of nitrogen gas to stir up surface material, and captured the debris. The blast worked so well that it collected more than expected, jamming the mechanism and causing some of the precious sample to leak into space before it could be secured. Despite the drama, the mission was a triumph. In September 2023, its capsule safely parachuted into the Utah desert, carrying the largest asteroid sample ever returned to Earth. These missions go beyond pure science. They are strategic steps in a much longer game. The overall mood of space resource utilization is crucial for the future of space resource utilization, mining water for rocket fuel or extracting rare metals. In this sense, these multi-billion-dollar missions are not just investments in knowledge, but in the infrastructure of a future off-Earth economy. Humanity is no longer merely a recipient of cosmic messages. We have become couriers ourselves, venturing outward to collect letters from the deep past. Long before the advent of mass spectrometry, electron microscopes, or robotic space probes, humanity's relationship with the stones that fell from the sky was forged not in the laboratory, but in the crucible of myth, religion, and fear. For our ancestors, a rock plummeting from the heavens was not a natural phenomenon to be analyzed, but a divine message to be interpreted. These objects were, at various times, worshipped as gods, feared as omens of war and famine, and treasured as priceless gifts from the celestial realm. This deep cultural history reveals as much about our own evolving worldview as it does about the meteorites themselves. In the ancient world, many cultures viewed these visitors with profound veneration. Perhaps the most famous and enduring example is the Black Stone, set into the eastern corner of the Kaaba in the Grand Mosque of Mecca. While its precise origins are a matter of theological and scientific debate, Islamic tradition holds that it fell from heaven to show Adam and Eve where to build an altar, and for centuries it has been revered by millions of pilgrims. In the 3rd century Roman Empire, the Emperor Elagabalus, formerly a priest from Syria, brought his local sun god, embodied in a conical black stone believed to be a meteorite, to Rome. He built a magnificent temple for it and declared it the supreme deity of the empire, a stark example of a meteorite becoming the central focus of state religion. This reverence was also rooted in a profound material advantage. Before humanity mastered the smelting of terrestrial ores to usher in the Iron Age, the only source of workable iron was from the sky. Meteoric iron, an alloy of iron and nickel, was an incredibly rare and precious material, literally a gift from the gods. Archaeological evidence for this heavenly metal is found across the globe. One of the most stunning examples was discovered in the tomb of the Egyptian boy king Tutankhamun. Resting on his mummy was an ornate dagger, its blade still sharp after more than 3,000 years. Analysis in the 21st century confirmed what many had long suspected. The blade was forged from meteoric iron, its nickel content a clear signature of its extraterrestrial origin. To the ancient Egyptians, this was a blade worthy of a pharaoh, crafted from a material that was rarer and more mysterious than gold. This pattern repeats across cultures, from the Inuit of Greenland, who used fragments of the Cape York meteorite to fashion tools and harpoon tips, to ancient Tibetan statues forged from the same celestial material. Owning a piece of meteoric iron was to wield a fragment of the cosmos itself. As worldviews shifted, particularly in medieval Europe, the interpretation of these events often changed from veneration to terror. A fireball tearing across the sky was no longer a gift, but a portent of doom, a sign of divine anger, or a harbinger of plague, war, or the death of a king. This superstition was dramatically captured by the fall of the Ensisheim meteorite in 1492. In a field outside the Alsatian town, a 280-pound stone meteorite slammed into the earth with a thunderous crash, an event witnessed by a young boy. The fall occurred just before a major war and was immediately interpreted as a sign of God's favor for the Holy Roman Emperor Maximilian I. The meteorite was declared a holy relic. It was moved into the town's church, and to ensure the powerful omen would not leave, it was bound with iron chains and secured to the wall, a prisoner of human superstition. For centuries it remained there, a symbol of the prevailing belief that the heavens directly intervened in human affairs, often with violent and unpredictable results. The transition from this world of myth and fear to one of scientific inquiry was not a smooth one. For much of the Enlightenment, the scientific establishment, including luminaries at the French Academy of Sciences, staunchly rejected the idea that rocks could fall from the sky. Reports from eyewitnesses, who were often rural peasants, were dismissed as folklore and superstition. The prevailing wisdom held that stones could not exist in the empty space of the heavens. This rigid skepticism was shattered on April 26, 1803. On that day, a brilliant fireball was seen over a large part of France, culminating in a violent explosion that rained down more than 3,000 individual stones on the town of L'Aigle. The event was so public and the evidence so overwhelming that it could not be ignored. The French government dispatched a brilliant young physicist, Jean-Baptiste Biot, to investigate. Biot conducted what is now considered the first modern scientific investigation of a meteorite fall. He systematically interviewed eyewitnesses, mapped the strewn field where the stones had fallen, and analyzed the rocks themselves, noting their unique fusion crusts and mineral composition. His detailed, methodical report provided the first irrefutable, scientifically credible evidence that the stones had an extraterrestrial origin. The L'Aigle event and Biot's subsequent report forced the scientific world to accept a new reality, giving birth to the science of meteoritics and forever changing our understanding of the solar system we inhabit. The methodical investigation of the L'Aigle meteorite shower by Jean-Baptiste Biot in 1803 marked the birth of a new science, one based on the rigorous, hands-on analysis of physical evidence. For the next 2 centuries, our knowledge of asteroids and comets was almost entirely dependent on the fragments that survived their fiery descent and could be studied in a laboratory. We were cosmic archaeologists, piecing together the story of the solar system from the sherds and remnants that chance delivered to our doorstep. But today, we are no longer passive recipients. The science of meteoritics has expanded into the broader field of planetary science, and its primary laboratory is no longer the Earth, but the vastness of space itself. Using an array of powerful technologies, we can now study, dissect, and characterize these objects from millions of miles away, conducting a form of remote forensics that would have been unimaginable to the pioneers of the 19th century. We no longer have to wait for the message to arrive. We can now read its contents long before it is sent. The cornerstone of this remote analysis is spectroscopy, a technique that allows astronomers to decipher the composition of an asteroid by analyzing the sunlight that reflects off its surface. Just as a prism breaks white light into a rainbow, a spectrometer breaks down the faint, reflected light from an asteroid into its constituent wavelengths. The surface of an asteroid is composed of various minerals, and each mineral absorbs and reflects sunlight in a unique way, creating a distinctive pattern of light and dark bands within its spectrum. This pattern is a spectral fingerprint, a unique chemical barcode that tells a detailed story. By matching these fingerprints to the known spectra of minerals and meteorite types on Earth, astronomers can classify a distant point of light with remarkable accuracy. They can determine if it is a C-type asteroid, a dark, carbonaceous body similar to the Murchison meteorite, and a likely carrier of organic compounds. They can identify it as an S-type, a stony body composed of silicate rock and metallic iron, the most common source of meteorites found on Earth. Or they can spot the rare and highly valuable M-type asteroids, metallic bodies believed to be the exposed iron-nickel cores of ancient, shattered protoplanets. This technique is so powerful that it allows us to build a family tree, linking specific meteorite groups found in our museums directly to their parent asteroid families still orbiting in space. While spectroscopy reveals what an asteroid is made of, another technology reveals what it looks like: planetary radar. Using colossal radio antennas like the Goldstone Solar System radar in California's Mojave Desert, scientists can beam a powerful, focused signal of radio waves at a passing near-Earth object. This signal travels through space, bounces off the asteroid's surface, and the faint returning echo is collected and analyzed. This is not a passive observation. It is an active interrogation of the object. The overall mood of this warm, friendly tone, fluid and easy to follow, like a light science podcast. Keep your voice clear and coherent, with a gentle intonation that is both intelligent and soothing. Use pauses when necessary. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The infrastructure for this remote forensic work, the massive radar installations, the advanced observatories, the powerful supercomputers needed to process the data, is expensive and is operated by a small handful of nations and international consortia. This scientific capability has direct geopolitical and economic implications. The data gathered for planetary defense is the very same data needed to identify the most promising targets for future asteroid mining. The spectral analysis that identifies an M-type asteroid for scientists also flags it as a potential multi-trillion-dollar source of iron, nickel, and platinum for a future space economy. In this new age, the characterization of these distant rocks is the first step in creating a strategic map for the future human expansion into the solar system. The remote characterization of asteroids using spectroscopy and radar is not merely an academic exercise in planetary science or a defensive measure against potential impacts. It is, with increasing urgency, the foundational work of a new and potentially revolutionary industry: asteroid mining. As humanity confronts the hard limits of our planet's finite resources, the same objects that were once feared as harbingers of destruction are now being viewed through a new lens, as celestial treasure chests of almost unimaginable wealth. The asteroid belt and the thousands of near-Earth objects that stray from it represents a repository of raw materials so vast that it could fundamentally reshape the future of our civilization, both on Earth and in space. This is the new gold rush, and its prospecting has already begun. The economic drivers behind this ambition are twofold, addressing critical resource bottlenecks both on our world and beyond it. Firstly, asteroids are incredibly rich in the strategic metals that underpin our modern technological society. The platinum group metals, PGMs, including platinum, palladium, rhodium, and iridium, are essential for everything from catalytic converters and automobiles to advanced electronics and fuel cells. On Earth, these metals are exceptionally rare and are concentrated in only a few geopolitical regions, making their supply chains vulnerable. A natural, Mel-type metallic asteroid, however, is believed to contain more platinum group metals than have been mined in the entire course of human history, with a potential market value measured in the trillions or even quadrillions of dollars. But the even more valuable commodity for building a true spacefaring economy is not metal, but water. Locked away as ice within the clay minerals of C-type asteroids, water is the single most critical resource for sustaining human life and industry beyond Earth. It can be purified for drinking, provide oxygen for breathing, and, most importantly, be split into hydrogen and oxygen, the most powerful chemical rocket propellant known. The ability to refuel spacecraft at in-orbit depots using water extracted from asteroids would slash the cost and complexity of deep space missions, effectively creating a self-sustaining infrastructure in space. In this context, water becomes the oil of the solar system, and the asteroids that carry it are the fueling stations on the interplanetary highway to Mars and beyond. The technological challenges of capturing and processing these resources are monumental, but no longer confined to the realm of science fiction. The leading concepts do not involve landing massive, crude industrial equipment, but rather deploying swarms of highly specialized robotic spacecraft. These missions would likely unfold in stages. First, a robotic prospector, similar to OSIRIS-REx or Hayabusa 2, would characterize the target asteroid up close. This would be followed by robotic miners designed for the specific environment. On a metallic asteroid, this might involve magnetic rakes that scrape off loose fragments, or optical mining, a technique that uses vast deployable mirrors to focus sunlight, vaporizing the rock and allowing valuable metals to be collected. For a water-bearing C-type asteroid, the entire body might be enclosed in a containment bag, which is then heated by solar concentrators to bake out the water vapor, which is then captured and cryogenically stored. Crucially, the initial processing would happen in situ. Bringing tons of raw ore back to Earth would be prohibitively expensive. Instead, the water would be split, the metals refined, and only the most valuable finished products would be sent on the long journey home, while the bulk of the material would be used to build and fuel further expansion in space. This audacious vision has ignited a new space race, one driven as much by private capital and national strategy as by scientific curiosity. The first wave of ventures, such as planetary resources and deep space industries, backed by Silicon Valley billionaires, demonstrated that the concept was attracting serious investment, though they ultimately struggled with the immense technical and financial hurdles. Today, a new generation of more focused startups is emerging, but the key players are the nations themselves. Countries are now jockeying for position in this future economy. The United States, through its Artemis Accords, is actively promoting a framework for the utilization of space resources, creating a coalition of nations committed to this goal. The small nation of Luxembourg, in a bold strategic move, established a comprehensive legal framework to recognize private ownership of resources mined in space, transforming itself into a global hub for the nascent space mining industry. Meanwhile, China's ambitious deep space exploration program, including plans for sample return missions from other asteroids and its robotic lunar activities, is systematically developing the very capabilities that would be essential for any future resource extraction efforts. This has brought the world to a complex legal and ethical crossroads. The overall mood of space declares that celestial bodies are not subject to national appropriation, but it remains silent on whether private entities can extract and own the resources they contain. This ambiguity is now being fiercely debated at the United Nations as humanity struggles to write the laws for a new economic frontier before the rush truly begins. For all our ambition to reach out and touch the asteroids, to harness their resources and unlock their secrets, we are simultaneously confronting a dangerous paradox much closer to home. The very region of space we must traverse to begin these journeys, the orbital highways around our own planet, is becoming an increasingly hazardous, invisible minefield. The popular conception of space as a vast, silent emptiness is a dangerous illusion. In reality, low Earth orbit is a junkyard, a chaotic swarm of objects moving at incredible speeds, where a collision with an object no bigger than a fleck of paint can be catastrophic. This threat is twofold, composed of both the natural, persistent rain of micrometeoroids and a rapidly growing cloud of man-made space debris. Together, they represent one of the most significant technical and geopolitical challenges for our future in space. The natural micrometeoroid environment has been a known hazard since the dawn of the space age. These are the tiniest remnants of comets and asteroids, dust-sized particles that perpetually drift through the solar system. While on Earth they settle harmlessly, in the vacuum of space they travel at hypervelocities of up to 70 kilometers per second. At these speeds, kinetic energy transforms a grain of sand into a projectile with the impact energy of a bowling ball dropped from a skyscraper. Satellites, spacecraft, and space stations are under constant assault from this cosmic dust. Over time, these impacts can degrade critical surfaces, crack solar panels, and cloud camera lenses. To survive this environment, spacecraft are built with sophisticated protection, such as the Whipple shield, a multi-layered defense where a thin outer bumper wall shatters an incoming particle, dispersing its energy before it can hit the main spacecraft body. Astronauts aboard the International Space Station regularly conduct spacewalks to inspect and repair damage from these tiny collisions, a constant reminder of the unforgiving nature of their environment. But this natural, manageable hazard is now being catastrophically overshadowed by a problem of our own making: artificial space debris. For more than 60 years of space activity, we have treated Earth's orbit as an infinite dumping ground. The result is a toxic legacy of over 100 million pieces of junk, ranging in size from spent rocket stages and dead satellites down to minuscule fragments of metal and paint. This orbital debris behaves just like natural micrometeoroids, but its concentration in the most economically and scientifically valuable orbits is far higher. This has given rise to a terrifying theoretical scenario known as the Kessler scenario, proposed by NASA scientist Donald J. Kessler in 1978. He theorized that once the density of debris in a particular orbit reaches a critical point, a single collision can create a cascade. The fragments from that initial collision increase the probability of subsequent collisions, which in turn create even more debris, leading to a chain reaction that could eventually render certain orbits completely unusable for centuries. We may be approaching that tipping point. The monitoring of this threat is a matter of global strategic importance. The U.S. The Space Surveillance Network, along with complementary systems from Russia, China, and Europe, uses a global network of ground-based radars and optical telescopes to track tens of thousands of the largest objects. This catalog is used to provide collision warnings to all active satellite operators, including the International Space Station, which must perform avoidance maneuvers several times a year to dodge incoming junk. This data, however, is a double-edged sword. The same systems used to track debris are used to monitor the active military satellites of other nations, making data sharing a sensitive diplomatic issue. The economic consequences are immense. The threat adds hundreds of millions of dollars to the cost of designing, building, and operating satellites, which must be shielded and carry extra fuel for maneuvers. The loss of a single critical weather or communication satellite to a debris strike could have cascading economic impacts on the ground. This has been exacerbated by the irresponsible actions of some nations. Recent anti-satellite or ASAT weapons tests, which involve deliberately destroying a country's own satellite with a missile, have created massive clouds of new, long-lasting debris, drawing widespread international condemnation for polluting a shared global commons. In response, a new industry is slowly emerging: active debris removal. Missions are now being designed by space agencies and commercial companies to act as orbital tow trucks, using nets, harpoons, and robotic arms to capture the most dangerous pieces of large debris and drag them down to burn up in the atmosphere. The same sky that holds the key to our future is now filled with the ghosts of our past. A stark reminder that if we are to truly become a spacefaring species, we must first learn to clean up after ourselves. While nations and space agencies deploy billion-dollar technologies to track and characterize asteroids in the void, a parallel effort is unfolding on the ground, driven not by governments, but by a rugged and resilient subculture of individuals, the professional meteorite hunters. These modern-day prospectors operate at the confluence of science, adventure, and commerce, scouring the most desolate landscapes on Earth in search of stones that have completed their fiery journey through our atmosphere. Their world is a stark contrast to the organized, state-funded expeditions in Antarctica. It is a competitive, often secretive, and fiercely independent pursuit. A treasure hunt where the prize is a tangible piece of the cosmos. The life of a meteorite hunter is one of patience, deep knowledge, and an unwavering tolerance for failure. Finding these cosmic needles in a terrestrial haystack is not a matter of luck alone. It is a discipline. The hunt begins not in the field, but with data. When a bright fireball is witnessed and reported, hunters spring into action, analyzing eyewitness accounts, security camera footage, and Doppler weather radar signatures, which can sometimes detect the falling stones. They use this data to triangulate a potential impact zone, known as a strewn field, an elliptical area where fragments from a meteor that broke apart in the atmosphere are scattered. They study geological maps to identify terrain where a dark rock might stand out, avoiding forests and areas with dark volcanic soil. Once in the field, their tools are a blend of the traditional and the technological. Many hunters methodically walk grids, their eyes scanning the ground for any anomaly. For iron-rich meteorites, a metal detector is the tool of choice, while others use powerful magnets attached to the end of a walking stick, a meteorite cane, to test any suspicious-looking rock. Increasingly, drones are being deployed to survey vast and inaccessible areas more efficiently. But the single most important tool is the human eye, trained over years to recognize the subtle but distinct characteristics of a meteorite. The dark, often scalloped fusion crust, the surprising density, or the glint of extraterrestrial metal, and to instantly dismiss the countless lookalikes that geologists call meteor wrongs. Certain environments on Earth are natural collection areas, not because more meteorites fall there, but because the conditions for preservation and discovery are perfect. The world's hot deserts are the epicenters of the modern meteorite rush. The arid climate of the Sahara in northwest Africa, the deserts of Oman, and the dry lands of the American Southwest prevent the stones from rusting and weathering away. The sparse vegetation and often pale, uniform terrain make the dark stones stand out. The Northwest Africa region, in particular, has become the single largest source of meteorites on the commercial market. Here, a complex network of nomadic peoples, local dealers, and international brokers has created a thriving, if largely unregulated, economy. A local finding a strange rock in the desert can sell it to a dealer, who then brings it to market where it receives an official NWA designation. While these stones often lack the precise find data that scientists cherish, they have made thousands of new specimens, including incredibly rare lunar and Martian samples, available to science and collectors that would have otherwise remained lost in the sand. This commercial aspect creates a world of high stakes and fierce competition, fraught with legal and ethical complexities. When a major witnessed fall occurs, it can trigger a literal race as hunters from around the globe descend on the location. The question of ownership is paramount. In the United States, the law is generally clear. A meteorite belongs to the owner of the land on which it is found. This leads to hunters negotiating access rights with ranchers and landowners, often offering a percentage of the find's value. In other parts of the world, the laws are ambiguous, creating a legal gray market that can lead to scientifically priceless specimens being smuggled out of their country of origin. This creates a persistent tension between the commercial hunter, who needs to sell their finds to fund their expeditions, and the academic community, which seeks to preserve and study these objects for the benefit of all humanity. Yet the relationship is often symbiotic. Hunters are responsible for the vast majority of new meteorite discoveries, providing a constant stream of new material for laboratories to analyze. To maximize the value of a significant find, a hunter will almost always send a small sample to a university for official classification. This scientific analysis provides the meteorite with a name and a pedigree, which in turn dramatically increases its market value, ensuring that even in this commercial world, science is an indispensable partner. Among the tens of thousands of classified meteorites recovered from deserts, ice fields, and farmlands across the globe, a select few have transcended the realm of mere scientific specimens. These are the titans of the meteorite world, legendary individuals who have earned a place in history through their colossal size, their improbable stories of discovery, or the revolutionary scientific secrets they contain. They are the natural monuments of the cosmos, each with a unique narrative that illustrates our profound and often strange relationship with these visitors from space. They are the great meteorites, and their stories are as compelling as the celestial journeys they undertook. In a natural field in Namibia lies the undisputed king, the Hoba meteorite. It is the largest single intact meteorite ever found on Earth, a monolithic slab of iron and nickel weighing over 60 tons, as much as a battle tank. Its story is one of accidental discovery. In 1920, a farmer, Jacobus Hermanus Brits, was plowing his field when his plow struck something immovable. Upon excavating the object, he realized he had uncovered a massive metallic stone. Unlike nearly every other major meteorite, Hoba was never moved to a museum. Its immense weight has kept it firmly rooted to the spot where it came to rest some 80,000 years ago, and it has since been declared a national monument of Namibia, protected in a custom-built amphitheater. One of its most enduring mysteries is the absence of any significant impact crater. Scientists theorize that its unusually flat, tabular shape caused it to act like a cosmic skipping stone, grazing through the atmosphere at a shallow angle and landing at a relatively low terminal velocity, preserving it whole. Half a world away, another iron giant tells a story not of geological mystery, but of human ambition and conflict. The Willamette meteorite, a 15.5-ton behemoth, is the largest ever found in the United States. But its modern story begins not with its impact, but with its discovery in 1902 by a Welsh immigrant and miner named Ellis Hughes. He found the conical, deeply pitted meteorite resting in a forest owned by the Oregon Iron and Steel Company. Recognizing its significance and value, Hughes embarked on an audacious and secretive plan. For 3 months, with the help of his son, he worked to move the colossal stone nearly a mile from the company's land to his own. He constructed a primitive wooden capstan and a log cart, moving the meteorite inch by agonizing inch. When his secret was finally discovered, it triggered a landmark lawsuit. Hughes argued he had a right to the meteorite as its finder. The company argued it belonged to them as the owners of the land on which it was originally found. The Oregon Supreme Court sided with the company, setting a legal precedent that still largely governs meteorite ownership in the United States. The meteorite was eventually purchased and donated to the American Museum of Natural History in New York, where it remains a star exhibit. But its story has another layer. To the Clackamas people native to the region, the meteorite, which they call Tomanoos, is a sacred object, a visitor from the moon that healed their people, and they continue to fight for its spiritual repatriation. While Hoba and Willamette are famous for their size and stories, the Allende meteorite is legendary for its scientific importance. On February 8, 1969, a massive fireball exploded over the state of Chihuahua, Mexico, showering the desert with thousands of fragments of a rare and priceless meteorite type, a carbonaceous chondrite. The Allende event was a scientific jackpot. It was the largest carbonaceous chondrite fall ever recorded, delivering an unprecedented amount of pristine material to researchers just months before the Apollo astronauts would bring back the first rocks from the moon. Allende is filled with large, white, irregular-shaped inclusions known as calcium-aluminium-rich inclusions, or CAIs. Analysis of these CAIs revealed them to be over 4.567 billion years old, making them the oldest known solid objects to have formed in our solar system. They are the very first mineral grains to have condensed out of the hot, swirling nebula that would eventually form the Sun and planets. Allende was effectively a Rosetta Stone for cosmology, providing the physical evidence that allowed scientists to date the birth of our solar system and understand its primordial chemistry. Finally, some meteorites are famous not for their size or science, but for their sheer unearthly beauty. The Fukang meteorite, discovered in China's Gobi Desert in 2000, is arguably the most beautiful extraterrestrial object ever found. It is a palisite, a rare type of stony iron meteorite in which gem-quality crystals of the mineral olivine are suspended within a matrix of solid iron nickel. When slices of the Fukang are cut thin and backlit, the translucent golden-green olivine crystals glow like a stained glass window from another world. This breathtaking beauty has also made it a target for the high-end collector market. While a main mass is preserved, much of the meteorite has been cut into slices and sold for enormous sums, highlighting the constant tension between preserving these cosmic wonders whole and the commercial demand that brings their beauty to a wider private audience. Each of these great meteorites tells a unique story of planetary geology, of human struggle, of scientific revelation, and of cosmic art, transforming them from simple fallen rocks into enduring legends. While the annual meteor showers like the Perseids and Geminids provide a reliable and gentle spectacle, a celestial clockwork that produces a few dozen shooting stars per hour, there are rare and extraordinary occasions when this gentle rain becomes a deluge. These are the meteor storms, awe-inspiring and sometimes terrifying events when the Earth passes through an exceptionally dense stream of cometary debris, causing the heavens to erupt in a cascade of thousands or even tens of thousands of meteors per hour. These are not mere celestial curiosities. They are generational events that have left an indelible mark on human history. transforming our understanding of the cosmos and reminding us that the seemingly tranquil sky can, on rare occasions, put on a display of overwhelming power and fury. The most legendary of these events in modern history was the Great Leonid meteor storm of 1833. In the pre-dawn hours of November 13th, the skies over North America exploded in a spectacle so intense that it became known as the night the stars fell. For hours, meteors rained down with a frequency that defied belief. Eyewitness accounts from across the continent paint a picture of both wonder and apocalyptic terror. People described the sky as being in motion, with streaks of light so numerous they seemed like a shower of fire or flakes of snow in a winter storm. The sheer scale of the event had a profound psychological and social impact. In a deeply religious era, many believed they were witnessing the end of the world, the literal fulfillment of biblical prophecy. People fell to their knees in the streets to pray, church bells rang out in alarm, and a wave of religious revival swept through communities in the storm's aftermath. But amid the panic, the seeds of a scientific revolution were sown. A Yale University astronomer named Denison Olmsted, after witnessing the event, meticulously collected eyewitness accounts from across the country. The overall mood made two crucial observations. First, that the meteors all appeared to originate from a single point, or radiant, in the constellation Leo. And second, that this radiant point remained fixed among the stars, proving the phenomenon was occurring far beyond Earth's atmosphere. His work, and that of others, led directly to the breakthrough understanding that meteor showers are caused by Earth intersecting with the debris trails of comets, transforming meteor astronomy from a subject of folklore into a predictive science. The Leonids, linked to the 33-year orbit of their parent comet, Tempel-Tuttle, would put on another, even more intense performance 133 years later. On November 17, 1966, astronomers and observers across the western United States witnessed a storm of breathtaking intensity. At its peak, which lasted for a little over an hour, the rate of meteors was almost impossible to count, with credible estimates from astronomers at Kitt Peak National Observatory in Arizona reaching an astonishing 40 meteors per second. That equates to a rate of 144,000 per hour. Observers described the sky as being filled with overlapping, silent streaks of fire, a celestial waterfall of light. Unlike in 1833, the reaction was not panic, but scientific exhilaration. The event was captured on film, its spectrum was analyzed, and the data collected provided definitive confirmation of the storm's cyclical nature. These storms are not just a historical or scientific curiosity, they have significant modern geopolitical implications. In the late 1990s and early 2000s, as comet Tempel-Tuttle once again made its passage through the inner solar system, the world space agencies prepared for the anticipated Leonid storms with strategic seriousness. A dense cloud of sand and pebble-sized particles, each traveling at over 70 kilometers per second, poses a lethal threat to the multi-billion-dollar satellites that form the backbone of our global communications, navigation, and intelligence infrastructure. A collision with even a tiny particle at that velocity can be catastrophic. In response, an unprecedented level of international cooperation took place. Satellite operators from NASA and the European Space Agency to the U.S. military developed threat models and implemented protective measures. The overall mood of a natural, friendly tone, fluid and easy to follow, like a light science podcast. Keep your voice clear and coherent with a gentle intonation that is both intelligent and soothing. Use pauses when necessary. The overall mood should be relaxed, engaging, and comfortable, perfect for bedtime reading and space narration. The tempo should be around 0.90. During the peak storm periods, many satellites were reoriented, turning their most sensitive optics away from the incoming meteor stream and positioning their solar panels edge-on to minimize their profile and reduce the risk of a debilitating impact. A meteor storm is now treated as a severe space weather event, requiring the same level of global coordination and risk mitigation as a major solar flare. A stark reminder that our technological civilization's dependence on orbital assets has made us newly vulnerable to these ancient celestial downpours. Once a meteorite is wrested from the desert sands or plucked from the Antarctic ice, its journey is far from over. It begins a new life as an object of intense scientific scrutiny, entering a world of clean rooms, electron microscopes, and mass spectrometers. It is in these pristine laboratory environments, far from the chaotic moment of its fiery fall, that the rock's deepest and most ancient secrets are meticulously coaxed into the light. The analysis of a meteorite is a multidisciplinary forensic investigation, a process that peels back the layers of its history, from the scorch marks of its atmospheric entry to the primordial dust grains from which it was born. This is where the true value of these celestial artifacts is unlocked, providing the ground truth that validates our remote observations and informs our understanding of the solar system's 4.6 billion-year history. The first step in any analysis is classification, and this begins with a simple yet revealing act: cutting the meteorite open. Using diamond-bladed saws in a sterile environment to prevent contamination, scientists slice through the dark fusion crust to reveal the rock's interior. This first look provides a wealth of information. Is the interior a solid mass of interlocking metallic crystals, revealing the Widmanstätten pattern unique to iron meteorites? Is it a chaotic jumble of rock fragments and inclusions? A breccia telling a story of ancient asteroid collisions? Or is it a dark, carbonaceous matrix full of the chondrules and calcium-aluminum-rich inclusions that are the hallmarks of a primitive, unaltered chondrite? A thin section of this interior, a slice of rock ground down until it is transparent, is then prepared for examination under a petrographic microscope. By passing polarized light through this slice, geologists can identify the specific minerals present: olivine, pyroxene, plagioclase, and observe their structure and relationship to one another. This mineralogical makeup is the fundamental basis for classifying a meteorite into one of over 100 distinct categories, each representing a unique parent body or geological process. Beyond this initial classification, the most powerful analytical tools are brought to bear, designed to read the chemical and isotopic codes written into the very atoms of the rock. The electron microprobe bombards the sample with a focused beam of electrons, causing the atoms within to emit X-rays at characteristic energies. By measuring these X-rays, scientists can map the precise elemental composition of the meteorite with microscopic detail, revealing the exact ratios of iron, magnesium, silicon, and other elements. To delve even deeper, a mass spectrometer is used to measure isotopic ratios. Isotopes are variants of an element with different numbers of neutrons. The specific ratio of oxygen isotopes, oxygen 16, 17, and 18 for instance, is like a cosmic DNA fingerprint, unique to different regions of the early solar system. By measuring this ratio, scientists can definitively distinguish a rock from Mars from one born in the asteroid belt, or even link a specific meteorite group to its parent asteroid. These isotopic systems also act as geological clocks. The overall mood, the warm, friendly tone. Scientists can precisely date the different stages of a meteorite's life: the age when its parent body first formed, the time of a major impact event that shattered it, and finally, its cosmic ray exposure age, how long it traveled through space as a small, unprotected fragment before its eventual capture by Earth. For those meteorites suspected of carrying the building blocks of life, like the Murchison or Allende, the analysis enters the realm of organic chemistry. Using techniques like gas chromatography mass spectrometry, scientists can separate and identify the complex carbon-based molecules locked within the rock's matrix. This is a painstaking process, requiring extreme measures to avoid contamination from the organic-rich environment of Earth. But it is this work that has led to the unambiguous identification of extraterrestrial amino acids, sugars, and nucleobases, the components of proteins and DNA. These discoveries provide the hard evidence that the ingredients for life are not unique to our world, transforming these dark, ancient stones into the most compelling evidence we have in the ongoing search for our own cosmic origins. For every genuine meteorite that ends its cosmic journey in a laboratory or a collector's display case, there are thousands of terrestrial imposters. These are the meteorongs, the countless ordinary rocks that, for one reason or another, capture the imagination of a hopeful finder and are mistaken for visitors from space. The desire to find a celestial object is so strong that it fuels a constant stream of inquiries to museums, university geology departments, and scientific institutions around the world. Geologists are inundated with emails, photographs, and hopeful packages containing these terrestrial lookalikes. This phenomenon is not just a scientific curiosity. It highlights the deep human fascination with the cosmos and the challenge of bridging the gap between public enthusiasm and the rigorous standards of scientific verification. Unraveling the stories of these meteorongs reveals the subtle but definitive fingerprints that separate the truly extraterrestrial from the merely unusual. The vast majority of suspected meteorites turn out to be common terrestrial materials. The most frequent culprits are industrial byproducts, such as slag, the glassy, often bubbly waste material from smelting ores. Its dark, melted appearance and high density make it a convincing imposter. Another common meteorong is magnetite or hematite, naturally occurring iron oxide ores that are heavy and strongly attracted to a magnet, two of the most widely known and often misleading characteristics of genuine meteorites. Construction materials, strange-looking sedimentary concretions, and dark, dense basaltic rocks are also frequent sources of confusion. What these objects share is a visual strangeness. They look out of place, leading the finder to conclude they must be from somewhere else entirely. The challenge for scientists is to gently correct this assumption without discouraging the public's valuable interest and engagement. To distinguish the real from the wrong, scientists and experienced hunters rely on a specific set of diagnostic criteria. While no single test is definitive, a combination of features can quickly build a strong case for or against a celestial origin. The most crucial and telling feature is the fusion crust. This is the thin, dark, glassy rind, often just a millimeter thick, that forms when the meteorite's outer surface melts during its high-speed atmospheric passage. It is typically black or dark brown and has a matte, eggshell-like texture, sometimes showing flow lines or thumbprint-like depressions called regmaglypts created by the ablating material. If a rock is broken open, the interior will almost always be a different color and texture from this dark crust. The absence of a fusion crust on a freshly fallen stone is a significant red flag. Another key indicator is density and magnetism. Many meteorites, especially the common chondrites and the irons, have a high concentration of extraterrestrial iron-nickel metal. This makes them feel unusually heavy for their size compared to most terrestrial rocks. It also means that the vast majority of meteorites will adhere to a strong magnet. While many Earth rocks are also magnetic, a non-magnetic stone is very unlikely to be a meteorite. For those who can look closer, the presence of metallic flecks of iron-nickel scattered throughout the interior of a stony meteorite is another powerful clue. Unlike shiny terrestrial minerals like mica, which flakes, these metallic grains have a solid, silvery glint. Finally, the absence of vesicles or gas bubbles is critical. Terrestrial volcanic rocks and industrial slag are often bubbly and porous. Meteorites, having formed in the vacuum of space, are almost always solid, dense objects. A rock full of tiny holes is almost certainly a meteor wrong. The process of official verification is the final crucial step. An institution like a university or a major museum will accept a sample for analysis. If the initial visual inspection is promising, they will perform the same kind of sophisticated laboratory tests described previously, making a thin section, using an electron microprobe to confirm the mineral composition and the specific nickel content of the metal. If the rock is confirmed to be a meteorite, it is submitted to the Meteoritical Society, the international body that serves as the official registrar of all known meteorites. It's given a natural name, often after the nearest town or geographical feature to its fall location, and its classification and story are published, officially entering it into the scientific record. This final step completes the journey, transforming a strange rock found in a field from a meteor wrong or a meteor maybe into a verified, scientifically priceless messenger from the cosmos. The fall of a meteor is often perceived as a silent spectacle, a streak of light that tears across the heavens without a sound. But for those rare individuals who have been close to a major fireball event, the experience is anything but silent. A meteor's violent passage through our atmosphere is a multi-sensory event, one that can generate a range of strange and powerful sounds that arrive at different times and through different physical means. From eerie, instantaneous hisses and pops to delayed, ground-shaking sonic booms, the sounds of a falling star are some of the most mysterious and awe-inspiring phenomena associated with these cosmic intrusions. They are the audible signatures of immense energy being released, a soundtrack to the violent physics of atmospheric entry. The most enigmatic of these sounds are the electrophonic phenomena. Eyewitnesses to extremely bright fireballs sometimes report hearing strange sounds, hissing, popping, crackling, or rustling noises at the very same moment they see the meteor. For decades, these reports were dismissed by many scientists as auditory illusions or psychological phenomena. The reason for the skepticism was simple. The meteor is burning up 50 to 100 kilometers high in the atmosphere. Sound travels through air at a mere 340 meters per second. Therefore, any audible sound, like a sonic boom, should take several minutes to reach the observer on the ground, long after the flash of light has vanished. A natural male narrator seemed to violate the laws of physics. However, modern science has provided a compelling explanation for these seemingly impossible sounds. The theory holds that the intense light and plasma trail of a very large, low-frequency fireball emits a burst of very low-frequency VLF radio waves. These radio waves travel at the speed of light, reaching the observer at the same instant as the visual light. While humans cannot hear radio waves directly, this powerful electromagnetic energy can interact with objects in the observer's immediate environment. Things like eyeglasses, aluminum foil, dry hair, or even blades of grass. The VLF waves cause these objects to vibrate or to create a small electrical discharge, producing a faint sound that the witness perceives as coming directly from the meteor itself. It is a form of transduction, with the natural environment acting as a giant, imperfect loudspeaker for the silent radio broadcast of the falling star. It is a rare and ghostly phenomenon, the sky speaking not through the air, but through the language of electromagnetism. Minutes after the electrophonic hiss has faded and the fireball has disappeared, a far more visceral sound may arrive: the sonic boom. Just like a supersonic aircraft, a meteoroid traveling many times the speed of sound creates a powerful shockwave in the atmosphere. This conical wave of compressed air travels outward from the meteor's path, and if the meteor is large enough and penetrates deep enough into the atmosphere, this shockwave will eventually reach the ground. Its arrival is not subtle. It can manifest as a series of loud, thunderous claps, a low, rolling rumble that can be felt in the chest, or a sharp, explosive bang that can rattle windows and shake buildings. The overall mood of sonic boom of such intensity that its shock wave shattered glass across 6 cities and was the direct cause of most of the injuries reported. The significant delay between seeing the light and hearing the boom is a profound and often disorienting experience. An observer sees the sky blaze with silent, brilliant light. The event appears to be over, a momentary flash in the vast silence of the heavens. Then, minutes later, the sky speaks with a voice of thunder. This temporal separation between light and sound creates a surreal 2-act drama. It is one of the few natural events that allows us to viscerally experience the immense difference between the speed of light and the speed of sound. The sky flashes, the air trembles, and then, in the long, echoing silence that follows, the true scale and power of the event finally begins to sink in. Beyond the visible light that paints a fleeting streak across the night sky and the audible sounds that echo minutes later, a meteor's passage leaves behind another, more subtle trace: an invisible disturbance in the electromagnetic environment of our planet. As a meteoroid vaporizes high in the atmosphere, it doesn't just create light and heat. It leaves behind a rapidly expanding trail of ionized gas. For a few brief seconds, this trail becomes an ethereal, temporary mirror in the sky, one that can reflect radio waves. This phenomenon, known as meteor scatter, has opened up a unique window into studying these objects, allowing us to see the countless meteors that are too faint for the human eye, and to monitor their constant influx, day or night, regardless of weather conditions. This process is the basis for a powerful scientific tool, meteor radar. Specialized radar systems on the ground continuously transmit a low-power radio signal up into the atmosphere. Most of the time, this signal simply continues out into space. But when a meteor, even one smaller than a grain of sand, burns up, the resulting ionized trail reflects a tiny portion of that radio signal back down to a receiver on the ground. Each of these returning echoes is a single meteor detection. By analyzing thousands of these echoes, scientists can build a comprehensive, real-time map of the meteor activity above. They can determine the trajectory, speed, and altitude of each meteor. And by observing over time, they can map the radiant points of meteor showers with incredible precision, even those that occurred during the daytime, and are thus completely invisible to optical observers. These radar systems are the tireless, all-seeing eyes of meteor science, providing a constant stream of data that reveals the true, relentless scale of Earth's interaction with interplanetary dust. This same phenomenon has been ingeniously exploited for decades by a global community of amateur radio operators, or ham radio enthusiasts. Using meteor scatter, they can achieve long-distance communication that would otherwise be impossible. A ham operator in one location can transmit a radio signal aimed at the sky. If their signal hits a momentary meteor trail at the right angle, It can be reflected back down to Earth hundreds or even thousands of miles away, where it is picked up by another operator. Because the meteor trails are so fleeting, lasting only a few seconds at most, this form of communication is a high-speed art form. Operators exchange brief coded messages in the short window that the celestial mirror exists, a practice known as meteor burst communications. During major meteor showers, when the frequency of trails increases dramatically, the opportunities for these long-distance contacts multiply, turning the annual celestial spectacle into a global radio event. On a strategic level, this same principle has been utilized for military applications. In certain scenarios, meteor burst communications can provide a secure and resilient method for transmitting data over long distances. Unlike satellite communications, which rely on predictable, vulnerable assets in orbit, the meteor trails are random, transient, and impossible to jam effectively. For brief, low-bandwidth data transmissions, such as sensor readings from a remote location, bouncing a signal off a meteor trail can be a robust and covert alternative. This application underscores a recurring theme in meteor science. A natural phenomenon, once the subject of myth and superstition, has been harnessed by technology, serving the purposes of scientific inquiry, passionate hobbyists, and strategic defense alike. The silent, invisible trails left by falling stars have been given a voice, carrying whispers of data across continents in the brief, shining moment of their existence. Not every meteoroid that encounters our planet is destined for a final fiery demise. On incredibly rare occasions, an object will approach Earth at such a shallow, grazing angle that it performs a celestial ricochet, dipping into the upper atmosphere, blazing like a conventional meteor, and then exiting back into interplanetary space. These are the Earth-grazing fireballs, or Earth grazers, arguably the most dramatic and improbable of all meteor phenomena. They are the ultimate near misses, cosmic stones skipping off the atmosphere like a flat rock across the surface of a pond. Their trajectories forever altered by the brief, violent encounter with our world. The physics of an Earth-grazing event are a delicate balancing act between speed, angle, and atmospheric density. The meteoroid must approach the planet at a tangent, entering the atmosphere at an angle so shallow that it passes through only the most tenuous upper layers. It must be traveling fast enough to maintain its cosmic velocity, but not so fast that the atmospheric drag is sufficient to capture it entirely. As it dips into the top of the atmosphere, typically at an altitude of 50 to 90 kilometers, it experiences the same immense heat and pressure as a normal meteor, creating a brilliant, long-lasting fireball that can travel for thousands of kilometers across the Earth's surface, visible to observers across entire continents. But instead of plunging deeper, its trajectory carries it back out of the thickening air, allowing it to escape Earth's gravitational pull and continue on a new, altered orbit around the Sun. One of the most famous and well-documented events of this kind was the Great Daylight Fireball of 1972. On August 10th, thousands of astonished eyewitnesses from Utah in the United States to Alberta, Canada, watched as a brilliant fireball, as bright as the full moon, blazed silently across the daytime sky. Captured on tourist cameras and even a U.S. Air Force satellite, the object, later designated US 1972-0810, was a car-sized asteroid that skimmed the atmosphere for 101 seconds, traveling over 1,500 kilometers before skipping back out into space. Had it entered the atmosphere at a steeper angle, it would have likely ended its journey in an airburst explosion with an energy comparable to the Chelyabinsk event. Its passage was a silent, beautiful, and sobering reminder of the near misses that occur, largely unnoticed, in our cosmic neighborhood. These events are more than just a visual spectacle. They are scientifically significant. The brief flash of its atmosphere acts as a brake, slowing the object down and altering its orbit. This means an Earth grazer that escapes could, on a future pass, be in an orbit that is more likely to result in a direct impact. The intense heat of the passage also modifies the object's surface, creating a temporary fusion crust and potentially changing its physical characteristics. From the perspective of planetary defense, an Earth grazer is a particularly challenging type of object. Its shallow approach vector can make it difficult to detect with ground-based telescopes until it is very close to Earth. The 1972 event, for example, was a complete surprise. It highlighted the importance of continuous all-sky surveillance to detect objects coming from unexpected trajectories. An Earth grazer is a cosmic ghost, a visitor that touches our world without truly arriving. It leaves behind nothing but a glowing trail in the sky and a lingering sense of wonder in those who witness it. It is a testament to the incredible energies and the knife-edge probabilities that govern the chaotic dance of objects within our solar system. The brief flash of its passage is a reminder that the boundary between a harmless, beautiful fireball and a devastating impact can be a matter of a few degrees, a silent, high-stakes ballet playing out in the heavens above. While Earth's dynamic geology and thick atmosphere work tirelessly to erase the evidence of its violent cosmic history, the other terrestrial worlds of our inner solar system are not so fortunate. They are silent, static museums of bombardment, their surfaces bearing the unhealed scars of billions of years of impacts. By turning our telescopes and robotic explorers, the Moon, Mars, and Mercury, we can see our own planet's past and appreciate the profound and unique protection our atmosphere provides. These worlds serve as control groups in a long-running solar system experiment, starkly illustrating what happens to a planet that faces the cosmic firing range without a shield. Our own moon is the most immediate and powerful example. Devoid of any significant atmosphere, wind, or water, the moon's surface is a pristine and brutal record of every major impact it has ever sustained. Its face is a chaotic tapestry of craters, overlapping craters, ranging in size from microscopic pits caused by micrometeoroids to vast, multi-ringed basins hundreds of kilometers in diameter, like the South Pole Aitken Basin, one of the largest known impact structures in the entire solar system. Because there is no erosion, craters that were formed billions of years ago remain almost perfectly preserved, their sharp rims and deep floors a testament to the violence of their creation. The lunar surface is, in effect, a fossil. It tells the story of the late heavy bombardment, a tumultuous period in the early solar system when the newly formed planets were subjected to a torrential rain of asteroid and comet impacts. Earth would have suffered an even more intense version of this bombardment, but while our planet's scars from that era have been completely erased by plate tectonics and erosion, the moons have survived, offering us our only direct window into that chaotic time. Mars, the red planet, tells a more complex and nuanced story. It has a thin atmosphere, about 100 times less dense than Earth's, which offers some minimal protection against the smallest meteoroids. The overall moon experiences winds that can create planet-circling dust storms and has evidence of ancient water flows, meaning that its surface is not as static as the moon's. As a result, its cratering record is a tale of two hemispheres. The southern highlands of Mars are ancient and saturated with craters, a landscape that rivals the most heavily battered regions of the Moon. In contrast, the northern lowlands are much younger and smoother, the result of vast volcanic plains that buried the older cratered terrain. This great dichotomy makes Mars a fascinating intermediate case between the Earth and the Moon. Its surface reveals a history of both intense bombardment and significant geological activity. Studying Martian craters has been crucial for our robotic explorers. Craters can act as natural drill holes, excavating material from deep beneath the surface and exposing ancient rock layers in their walls, providing a tantalizing glimpse into the planet's geological and perhaps even biological past. Perhaps the most extreme example of cosmic bombardment is Mercury, the innermost planet. With no atmosphere to speak of and a surface that has been largely geologically inactive for billions of years, Mercury's face is, like the Moon's, almost completely covered in impact craters. Its proximity to the Sun means that it orbits in a region of space where objects are traveling at much higher velocities, leading to more energetic and destructive impacts. Mercury's most dominant feature is the Caloris Basin, a colossal impact crater some 1,550 kilometers in diameter, so large that the seismic waves from its formation are believed to have traveled through the entire planet, creating a bizarre jumbled landscape of hills and fractures on the exact opposite side of the globe. These other worlds, frozen in time, are a powerful reminder of a fundamental truth. Impact cratering is not an exception in the solar system. It is the dominant geological process. The relative scarcity of craters on Earth is the true anomaly, a direct and life-sustaining consequence of the thin, blue line of our atmosphere and the restless, healing skin of our planet. While Earth's active systems erase the vast majority of its impact scars, some collisions are simply too large to hide. These are the mega-impacts, events of such titanic scale that their fingerprints are permanently branded into the continental crust, surviving for billions of years. These structures are more than just craters. They are vast, complex geological provinces that tell a story of planetary trauma and surprising rebirth. They reveal the upper limits of Earth's resilience, and in a recurring theme of cosmic irony, have often become sites of immense resource wealth, their violent origins directly responsible for creating treasures that would later fuel entire industries and shape the economies of nations. Examining these giant terrestrial impact structures is to read the gravest chapters of our planet's history. The largest and oldest confirmed impact structure on Earth is the Vredefort Dome in South Africa. What we see today is not a crater, but the deeply eroded central uplift of a colossal impact that occurred over 2 billion years ago. The original crater, now long vanished, is estimated to have been up to 300 kilometers in diameter. Created by an asteroid or comet thought to be 10 to 15 kilometers wide, an object even larger than the one that killed the dinosaurs. The impact was so powerful that it punched through the crust and caused the mantle itself to rebound, creating a dome of granite 90 kilometers across. Today, this dome forms a striking ring of hills that has been designated a UNESCO World Heritage Site for its unique geological significance. The Vredefort impact occurred in a region that is now home to the Witwatersrand Basin, the source of nearly half of all the gold ever mined on Earth. While the impact did not create the gold, the immense structural upheaval it caused is believed to have helped preserve these ancient gold deposits, tilting and burying them in a way that protected them from erosion for billions of years until they were discovered by humans. A similar story of cataclysm and creation can be found in Canada at the site of the Sudbury Basin. About 1.8 billion years ago, a comet or asteroid approximately 12 kilometers in diameter slammed into the ancient Canadian Shield. The impact created a transient crater nearly 200 kilometers wide and flash melted a vast volume of the Earth's crust, creating a sea of superheated magma. As this enormous melt sheet cooled over thousands of years, heavy ore-bearing minerals sank and became concentrated at the bottom. The result is the Sudbury Igneous Complex, one of the richest and most important mining districts on the planet. From this single ancient scar, humanity has extracted vast quantities of nickel, critical for producing stainless steel and modern batteries, as well as copper, platinum, palladium, and other precious metals. The city of Sudbury exists because of this impact. Its economy and a significant portion of the world's strategic metal supply is a direct legacy of a cosmic collision that occurred when the most complex life on Earth was still single-celled. These megastructures are our only terrestrial laboratories for understanding the environmental effects of truly planetary-scale impacts. Scientists study the shocked rocks, the vast melt sheets, and the distorted crustal layers to model what happens when an object overwhelms all of our planet's defenses. The energy released from the Sudbury impact, for example, would have vaporized vast amounts of rock, ejecting a plume of superheated gas and dust that would have circled the globe, drastically altering the climate for centuries. The seismic shock would have registered as a magnitude 12 or 13 earthquake, triggering secondary volcanism and global tsunamis. By studying these ancient events, we gain a more complete picture of the Chicxulub impact and can better prepare for the potential consequences of a future threat. These colossal scars are the ultimate ground truth, a permanent record written in stone that reminds us that while our planet can heal, it never truly forgets. We have journeyed through the past, from the formation of the solar system to the dawn of human understanding. We have explored the present, witnessing the global effort to track, analyze, and prepare for the ever-present cosmic threat. Now we must confront the future. We must ask the ultimate question: what would happen if, despite all our efforts, a major impact event were to occur in our lifetime? What would be the cascading consequences of a collision with a moderate-sized asteroid, an object large enough to penetrate our atmosphere, but not big enough to cause a mass extinction? This is not an exercise in fantasy, but a critical strategic simulation, a scenario that governments, scientists, and emergency response agencies around the world are now forced to contemplate with the utmost seriousness. Let us imagine an object 500 meters in diameter, more than twice the size of the asteroid that carved the famous Barringer crater in Arizona, is on a collision course with Earth. The overall mood would be marked by a terrifying certainty, with the impact location pinpointed to a specific region. The event itself would defy all modern comparison. If it were to strike a landmass, the impact would release energy equivalent to tens of thousands of megatons of TNT, dwarfing the entire global nuclear arsenal. It would excavate a crater nearly 10 kilometers wide and 2 kilometers deep, instantly vaporizing everything at ground zero. The seismic shock wave would register as a magnitude 7 or 8 earthquake, devastating an area the size of a small country. A cloud of superheated dust, ash, and vaporized rock would be ejected into the atmosphere, creating a plume that would rise into the stratosphere. The immediate aftermath would be a scene of regional apocalypse, but the cascading global consequences would be even more profound. If the impact were to occur in the ocean, it would trigger a mega tsunami. Unlike a tectonic tsunami, which is a long rolling wave, an impact tsunami would be a more chaotic and complex event, with waves potentially hundreds of meters high, radiating from the impact site, capable of inundating coastlines thousands of kilometers away, and wiping out major coastal cities. The vast amount of water vapor and sea salt blasted into the stratosphere would have significant, unpredictable effects on the global climate. Whether on land or at sea, the sheer quantity of dust and aerosols injected into the upper atmosphere would begin to block out sunlight, a phenomenon known as an impact winter. Global temperatures would plummet. Agriculture would collapse. The world's interconnected just-in-time supply chains for food, medicine, and energy would be shattered. The overall meteors is, in the end, the story of our own maturity as a species. It is the story of our transition from being helpless victims of circumstance to becoming the active guardians of our own planet, a responsibility we are only now beginning to fully comprehend.